In the previous lecture, we looked at the TEM mode solution on parallel plate waveguide. But as I've been indicating to you, there are many different solutions to the Helmholtz equation that can satisfy the same set of boundary conditions, and each of these represents a mode, and these modes can be simultaneously present. We're going to look at examples now of the transverse electric and transverse magnetic modes that also exist on parallel plate waveguide. The learning objectives for this lecture is, first of all, that students be able to understand how the TE and TM mode solutions come from the wave equation. Just like in the previous lecture, we looked at how the TEM solution resulted from the Helmholtz equation. Now we're going to look at a slightly different solution. Students need to comprehend the characteristics of these two types of modes, what are their key distinguishing features, and how they differ from the TEM mode. And you need to be able to analyze wave properties in waveguide if you're given the parameters of the mode, and be able to calculate things like modal impedances, group velocity, phase velocity for these modes. So just like we did in the TEM case, we're going to start with our parallel plate boundary conditions, and we're going to satisfy the Helmholtz equation, and we're going to satisfy the Helmholtz equation subject to the boundary conditions associated with the parallel plate. As we did in the previous lecture, we need to postulate solutions to the Helmholtz equation and then be able to determine the requirements that allow those particular solutions to satisfy the boundary conditions that we care about. So the solutions we're going to start with are the transverse electric solutions. And this is another example beyond the TEM mode of things that can propagate on a parallel plate transmission line. We're going to require that only the electric field be transverse in this instance. So we'll say that the electric field as a function of position will have this form. It'll have an x component and a y component. We're going to say that the fields can only vary as a function of y, because we're going to, as we did in the previous lecture, we're going to treat this as a very wide waveguide where the separation d is small compared with the width w. So we're going to neglect any variability in the horizontal direction. As we know, when we get near the edges, we know that field variation is going to be introduced, and we're going to ignore that. As we did in the TEM mode case, we're going to assume that the only z variation is e to the minus j beta zz. But I want to caution you, we're going to find out that this beta z is different than the beta z we saw for the TEM mode. And furthermore, we're actually going to find that there are many different TE modes, and each of those TE modes has a different value for its beta sub z. Right? So with these restrictions on the transverse electric field, we can now come in and say, well, once again, we can exploit the fact that the divergence of E must be equal to 0. And so if the divergence of E must be equal to 0, we can have two ways that this can be satisfied. One way is if the electric field is constant. However, when the electric field is constant, we have the TEM mode solution, because we saw that in the previous lecture. So the other way that we can possibly have a transverse electric solution would be for us to have an x-polarized component of the field that varies as a function of y. If I take this expression and plug it in up above and then take the divergence, we'll see that this has no contribution to the divergence of the field. So if we assume then that the x-polarized component of the electric field has this behavior, and that there is no y-polarized component, and there is no z-polarized component by definition, because this is a transverse electric mode, then we can write down using Maxwell's equation what the magnetic field is. We take the curl of E, we divide by -1 over j omega mu, and we end up with a y component and a z component. So we have an electric field that's only polarized in the x direction. We have a magnetic field that's polarized in the y direction. And then we also have a longitudinal magnetic field component that's expressed here. So if we're able to solve for E sub x, then we can determine what our magnetic field is through these expressions, and we end up with something that takes this sort of a form, where we have the 1 over j omega mu up front. When we take the derivative of x with respect to z, we get the minus j beta. When we take the derivative with respect to y, we get whatever it is we end up getting. So now we need to exploit our boundary conditions, right? So we have a solution that satisfies the Helmholtz equation, satisfies Maxwell's equation. We're now going to need to find out what characteristics of the solution allow us to get answers and how they can obey the boundary conditions. Just as we did in the TEM mode solution, we're going to treat ourselves as having lossless dielectrics with permeability mu and permittivity epsilon between our plates. Our separation is D, our width is W, and while it's not drawn this way, we're going to make the assumption that D is much, much less than W. So when we evaluate this Helmholtz equation, the first thing we can do is we know we can take the z derivative. As we saw on the previous slide, when we take the two z derivatives, we're going to get a minus j beta squared. And when we get that minus j beta squared, we end up with the x derivative, the y derivative of the x component plus this quantity here. So remember, beta is the wave number of the medium. So it is omega square root of mu epsilon. Right? So we can come in here and say that beta equals omega square root mu epsilon. It's a function of the material. Okay? Beta sub z is one of the unknowns that we're trying to solve for. So we don't know what beta sub z is yet, but we know that when we take our two z derivatives, it's going to come down here. And I can call this entire quantity beta sub y. Right? Make that replacement. Right? And it's just a number. It's a constant. And when I define this as beta sub y squared, I should say, I end up with this equation that we see down below. But this is an equation that we're familiar with. We know what its solutions look like. Right? Its solutions take the form of sines and cosines. Right? So we've reduced our Helmholtz equation down to this second order ordinary differential equation. It has solutions that we know, and our job now is to use the boundary conditions to figure out values for A, B, and beta from our boundary conditions. So the first boundary condition we're going to apply is that the x component of the field must be equal to 0 and y equals 0. Why is that the case? Well, we'll remind ourselves. Right? At a perfect electrical conductor, E tangential must be equal to 0. Right? And the tangential directions are E sub z and E sub x. Now there is no E sub z because we stipulated that this is a transverse electric mode. So we have E sub x equals 0. And at y equals 0, we get cosine of 0 plus sine of 0. Well, that goes away, so it doesn't cause us any trouble. But this cosine of 0 is, of course, equal to 1. And the only way I can satisfy this equation is if a is equal to 0. And so if I set a equal to 0 by enforcing that boundary condition, this bit goes away. And now my expression for the x component of the electric field is b times sine beta, y times y. So next we apply the boundary condition at the top interface. And at the top perfect conductor, the tangential component must be 0 again. So I substitute in y equals d here. Right? You see y equals d. And the only way for this to be true is if beta y times d is an integer multiple of pi. It can be 0 pi, 1 pi, 2 pi, 5 pi, 37 pi. It doesn't matter. So long as beta y times d is an integer multiple of pi, then the sign is going to be 0. So this now gives us an infinite number of potential solutions, one for every integer n. We can then take beta sub y, which we've now determined, and for any particular mode, any particular value of n, we said beta y was equal to beta z. This term here was equal to beta y squared. So we can invert this and get a solution for beta z, which we'll write down below. Beta z is equal to omega squared mu epsilon minus beta y squared, or omega squared mu epsilon minus n pi over d, quantity squared. So as n increases, the argument underneath the square root is going to decrease. And that's a very important property of these transverse electric and transverse magnetic modes. They have a different beta sub z for every value of n. Though, as we just said, we have many different solutions to the Helmholtz equation, one for each integer n. When I specify a given value of n, I have a coefficient that goes with it, right? So n equals 1, I'm going to have b1. N equals 2, I'm going to have b2. These two modes both satisfy the boundary conditions. They can both be present at the same time by superposition. And which modes I have depends upon how I excite the system. So if this is my x component of the electric field for the nth mode, I can then plug that into my equations and get the y component of the magnetic field for the nth mode. And in order to get that, I have to take the derivative with respect to z. And then I can get the z component by taking the derivative with respect to y, and the sign becomes a cosine. And the n pi that shows up here. And so this ends up being our method for determining all three of the field components given our solution for only one of them, right? So the key here is that we solve for one field component, and after we solve for it, it gave us the other two for no extra charge or minimal extra charge, just had to do some algebra. We know what beta sum z is equal to. Some properties of this mode that we should highlight. First of all, the x component of the electric field and the y component of the magnetic field are in phase, both in space and in time, right? We see that they both vary like sine. They have the same argument. So they're increasing and decreasing with each other. However, the z component of the magnetic field is 90 degrees out of phase with the other two. Both in space, right, because the z component varies as a function of cosine instead of sine, so that's a 90-degree phase shift. And in time, because the z component of the field has this minus j, and we know that when we convert that back into the time domain by multiplying by e to the j omega t and taking the real part, that multiplying by j is a 90-degree phase shift. I can take the ratio of the x component of the electric field to the y component of the magnetic field and define that as a modal impedance, and that modal impedance is omega mu over beta sub z. Right? And this is actually the same exact form as we had for a plane wave, except for a plane wave we replace beta z by omega square root mu epsilon, and I end up with the impedance being the square root of mu over epsilon. But now that our modal propagation constant has changed, the modal impedance changes. The time average Poynting vector at each position in space is given by the 1/2, the real part of E cross H star. Right? What you see here is since E, X, and HY are in phase, they're going to give us a piece of the time average Poynting vector in the Z direction. It's going to be real. And when I take EX, cross it into HZ, that's going to give me a component of the Poynting vector in the Y direction, but it's going to be purely imaginary. So it's not going to contribute anything to the time average Poynting vector. Let's spend a little bit of time now talking about this propagation constant. We've seen this propagation constant before. You saw it in the transmission line section of the course. We've already introduced it and discussed it in the plane wave propagation section of the course. But up until now, this beta sub z, the propagation constant in the direction of propagation, has been dictated solely by the material properties, solely by the permeability and permittivity. But now we see something a little bit different. We now see that for the TE and TM modes on a waveguide, that beta z has this behavior. Right? So I plotted here on this chart, this dotted line is beta sub z for a plane wave, right? Where it's just omega equals beta over square root of epsilon. So it's just a straight line. I'm plotting omega as a function of beta. But in the solid line, I plotted this expression here, and we see something very interesting. Right? For high frequencies, the behavior of the omega beta curve, or what we call the dispersion diagram, looks very similar to what we get in a plane wave. But as my frequency decreases, eventually I get significant divergence between omega and beta, even down to the point where I have this interesting property here. What happens here? Well, at that point, my frequency is such that for this particular mode, n is large enough that this quantity I've just highlighted is actually less than 0. I take the square root of something that's less than 0, and I get a purely imaginary propagation constant. So beta to z becomes imaginary, and then when I look at e to the minus j times a imaginary thing times z, I end up with what we call an evanescent mode, or a mode that decays exponentially. And so I have that behavior here. Right? So the propagation constant is purely imaginary, and I get beta sub z equals minus j alpha. And when I substitute it into the e to the minus j beta z times z, I end up with something that decays exponentially. What this means is, for that frequency, the mode is cut off. And over here on this plot, what that's saying is that as I decrease my frequency towards 0, eventually I'm going to get to a frequency below which the mode does not propagate. And we call that the cutoff frequency for this particular mode. We can compute what that is from our dispersion relationship that we have here. The cutoff frequency for the nth mode is given by this expression. Interestingly, it corresponds to the cutoff frequency associated with an integer number of half wavelengths that fit inside the waveguide. So for the first mode becomes cut off when the free space wavelength is more than half a wavelength. I keep reducing my frequency until the wavelength gets too long. The n equals 2 mode, that's cut off until I increase my frequency to the point where I can fit a full wavelength inside the parallel plates, and so on and so forth. So we just computed a set of modes associated with the transverse electric condition, and we can do a similar thing for the transverse magnetic condition. We'll assume now that the magnetic field is completely transverse. Right? So if the magnetic field is completely transverse, we have this sort of assumed form. There's no z component. Since divergence of h is equal to 0, when we look at this behavior, divergence of h, of course, is the derivative of the x component with respect to x plus the derivative of the y component with respect to y plus the derivative of the z component with respect to z. But there is no z component, and this term doesn't vary as a function of x. So the only way we can have that is to have the derivative of h sub y with respect to y be equal to 0. Either that means h sub y is equal to a constant, or h sub y is equal to 0. But h sub y being equal to a constant, having a constant y component of our magnetic field, would mean that I'd have a non-zero normal component of magnetic field at that perfect conductor, and I can't have that. Right? So that means that our details of the problem are going to tell us that the y component of the magnetic field must be equal to 0. And that means that our solution has only the x term. Once we've stipulated, or once we've determined that the H field has only its x component, we can plug it into the Maxwell's equation to get the electric field in terms of the x component. And just as we saw in the TE case, we have an expression of this form. Once I solve for h sub x, I can use it to compute the y and z components of my electric field. And they have this functional behavior. We can go through an identical set of steps of applying our boundary conditions at those interfaces. Now in this case, though, our H field is completely tangential, so the tangential H field is not going to help us. We're going to need to use the tangential electric field, which we get from taking the derivative, in order to be able to determine what our boundary conditions are. When we do that, we end up with a TM mode that satisfies this particular set of relationships. Again, I can choose many different values of M. In the TE case, we had a modal impedance that was given by omega mu over beta. In the TE case, in the TM case, we have beta over omega epsilon. So we have a similar sort of behavior. This gives us the ratio of E to H. This modal impedance is going to be E sub Y over H sub X. Okay. The time average pointing vector, instead of having a sine squared behavior, now has a cosine squared behavior that we get from these terms. The cutoff frequency has exactly the same form. The cutoff frequency is determined by the mode index, and the cutoff frequency corresponds to the frequency whose wavelength is an integer number of half wavelengths that fit inside the waveguide. But in this case, I want to highlight something. The special case of m equals 0. Let's take a look at what happens when I stick in m equals 0 into these equations. Well, when m equals 0, this gives me sine of 0, and the e sub z component goes away. When m equals 0, this cosine becomes 1. This cosine becomes 1. And I have an electric field, which is a constant, times e to the minus j beta z. A magnetic field, which is a constant, times e to the minus j beta z. And the ratio between the electric and the magnetic fields is the wave impedance of the material. So the m equals 0 transverse magnetic mode is the special case of the TEM mode. Right? We did the TEM mode first from a different set of arguments, but it corresponds to a special case of the TM solution. So, what are the key elements to take away from this lecture? There's a few. 1. It is possible to have discrete sets of transverse electric and transverse magnetic modes. There was only one TEM mode, but in addition to that TEM mode, I now have an infinite number of potential TE modes and an infinite number of potential TM modes. Right? By enforcing the Helmholtz equation and the boundary condition, we get a set of modes that have amplitudes that are, in this case, oscillating as a function of y, either like sine or cosine, depending upon whether it's a TE or a TM mode. The more oscillations that I get, right, because I had sine of n pi y over d, the higher value n is, means the more oscillations that I have within that d distance. That means the cutoff frequency becomes higher for that particular mode. Each mode propagates with a different phase velocity. Okay? In the tutorial, what I want you to do is spend a little bit of time looking at the cutoff frequency in the dispersion diagrams. So given that you know how omega varies as a function of beta, and given that you know how to compute the phase velocity and the group velocity, you should be able to exercise that for the various TE and TM modes to figure out which ones are propagating any given frequency. The second thing is I'm asking you to do something that's interesting. We've already looked at the example of what happens if I have two plane waves propagating at slightly different angles. And what I want you to look at is I want you to look at those two plane waves that are propagating at slightly different angles and allow them to interfere with each other. And what you're going to find is that we have just derived the TE and TM modes in terms of the field conditions, but you could also derive the TE and TM modes as a superposition of two plane waves traveling at oblique angles and allowing them to interfere with each other in such a way that you get satisfaction of the boundary conditions.